Okay, if you'll find your seat, we're going to start here in 30 seconds. We're going to start faster than that. Good morning, my name is Jason Moore. I'm the immediate past president for the Pile Driving Contractors Association. It's my pleasure to welcome you to IFCEE 2021 and our presentation this morning. It's really good to see all of you here. I also want to welcome those who are attending IFCEE virtually. Your online presence is a big boost, not only to the event, but also to the reason we're here this morning to present the PDCA E.A.L. Smith Award Lecture. First, allow me to provide some background about the E.A.L. Smith Award Lecture. This award honors E.A.L. Smith, who developed the wave equation analysis concept as a practical and useful tool for the pile driving professional. Additional development work added to the usefulness of the original approach. However, Smith's original development work remained at the center of modern versions, giving evidence of Smith's genius. Smith, a mechanical engineer by education, was chief mechanical engineer for Raymond International, a company whose main product was the step-tapered mandrel-driven pile. This economical type of deep foundation posed major challenges to the analyzing engineer, such as modeling non-uniformities and pin-mandrel connections. At the same time, working for a contractor made Smith conscious of the need for an easily understood, rational, and realistic analysis, and he excelled in meeting that requirement. Smith's ingenious solution to the pile driving simulation problem enabled pile driving contractors to optimize pile driving equipment, reducing the frequency of excessive installation times due to unexpected hard driving and pile failures due to excessive driving stresses. Smith stated, "I provided the engineer with a tool that helped design driven piles not only for geotechnical or structural suitability, but also for drivability and therefore constructability." Considering the benefits derived from Smith's work, the PDCA E.A.L. Smith Award Lecture awardee should be an individual who has demonstrated creative and original work that helped the driven pile industry provide an economical, sustainable, effective, and environmentally conscious foundation solution. The creativity can be demonstrated in the form of innovative foundation design, manufacturing, installation, or construction procedures. With this information setting the criteria for today's award, I'd like to ask the current PDCA President, Kevin Gouge, to come up and present the award.
Thank you, Jason, and good morning, everyone. I'd like to echo Jason's comments that we really appreciate all of you, both in person and virtually, being here this morning to honor our PDCA E.A.L. Smith Award Lecture recipient. Dr. Frank Rausche, PhD, professional engineer, has been involved in the research and development of dynamic testing and analysis methods since the mid-1960s. He started his engineering education in Stuttgart, Germany, and received his PhD in geotechnical engineering from Case Western Reserve University in Cleveland, Ohio, where he began as a researcher and later served as assistant professor. Dr. Rausche has developed the original CAPWAP program in 1969 and subsequently its continued improvements. He devised the case method capacity and integrity formulas and was co-developer of the pile driving analyzer, making dynamic pile testing a routine practice. Dr. Rausche was co-principal investigator in the development of the WEEP wave equation program for FHWA in 1976 and was principal investigator for its update in 1981. He then developed the GRL WEEP for personal computers in the 1980s and continues contributing updates. In addition to research in pile dynamic measurements and analysis, Dr. Rausche was one of the original founders of GRL Engineers Incorporated, a professional engineering firm established to provide specialized testing, analysis, and consulting services to the deep foundations industry. Serving as president from 1977 to 2011, Dr. Rausche continues today as a senior consultant for GRL and Pile Dynamics Incorporated. Throughout his years with GRL, Dr. Rausche traveled the world providing foundation testing services and educating engineers on dynamic testing methods. He holds numerous industry patents and has authored well over 100 papers on testing, design, and analysis of deep foundations published in journals and conference proceedings. Dr. Rausche has been highly recognized for his contributions to the deep foundations industry, receiving the ASCE 2000 Civil Engineer of the Year Award the 2003 DFI Distinguished Service Award, the 2009 G. Brooks Ernest Award from the Cleveland section of the American Society of Civil Engineers, the DFI 2015 Osterberg Memorial Lecture Award, and the Shannon and Wilson 2016 Stanley D. Wilson Memorial Lecture. He is a licensed professional engineer in Ohio and Colorado. He has achieved expert level on the PDCA PDI Dynamic Measurement and Analysis Proficiency Test and holds a Foundation Quality Assurance Expert Certificate in Data Acquisition and Data Interpretation for High-Strain Dynamic Testing, pile testing. Dr. Rausche is also a member of ASCE, DFI, and PDCA. Dr. Rausche, would you please join Jason and me on stage? Dr. Rausche, on behalf of the officers, board of directors, and the members of the Pile Driving Contractors Association, it is my honor and it gives me great pleasure to present to you the 2001 PDCA E.A.L. Smith Award Lecture.
Thank you.
This award is presented in recognition of his ceaseless efforts and dedication to advance the driven power industry through innovative, highly efficient, and environmentally sensitive solutions. Congratulations, Dr. Rausche. Would you please join me in giving him a hand? We need a picture.
We'll get out of your way.
Want to take one more picture, Jason, I think. All right. The podium is yours.
All right. Now, that was quite an introduction. Thank you very much. I learned a lot about what I did in this 60 years or so that since George Goebel called me to Case Institute of Technology at the time and said, what kind of a project do you want to work on? And I told him on something with concrete. And he says, that's not good. And I said, the only thing you have is this pile project. And he says, the pile project. Yes, that's good. You stay with me and do the pile project. So since then, I'm in the pile project. And it's great that the PDCA invites me here, being a pile tester that tested piles all my life. So that testing was going on in quadruplet. And thank you for inviting me, of course, also for the award and inviting me to talk about this subject. And actually something that came then about naturally when we developed the wave equation analysis and got involved with the wave equation according to E.A.L. Smith, in whose honors this award has been given. I will talk a little bit about Smith himself, about the history of the wave equation analysis, and give you, besides an introduction into the model and some other models of wave equation solutions, then some examples and some new developments and a summary. So one of the things that we have to do when we talk about wave equation, even though the PDCA hates it, is we have to talk about the wave equation. I mean, that's what it is all about. And there is this partial differential equation. It's a linear one. It's about the simplest one that there is. And of course, for us, it has to be simple and straightforward. And it involves a particle of the pile, W, that moves down the pile at a certain speed. And practically what it expresses is Newton's second law, namely that rho times the second derivative with respect to time, which is acceleration, mass times acceleration equals force. That's all it is. And this elastic modulus is important, together with the mass density. And if you take their ratio, then you get the wave speed. And that makes it easy to solve that equation. And that gives us then this solution of superposition of waves. And actually, with the wave equation, it doesn't, with a wave equation according to Smith, it doesn't come out really well that you have a downward traveling wave and an upward traveling wave of the displacements, the velocities, the accelerations, the forces, and the stresses. They are all in two parts of upwards and downwards traveling waves. So, you might wonder why I came to this conclusion here that Einstein had come to. Well, let's look at the various quantities here that go in the wave equation. The elastic modulus, the mass density, the wave speed, the area A, the length of pile L. And then if you figure the volume of the pile, that's A times L, and multiply it with the rho, the mass density, you get the mass of the pile. That's what the contractor gets paid for usually. And then that means that the mass of the pile is equal to ALE over C squared. And so now it dawns on you what Einstein had invented. E.A.L is nothing but energy. That's why the Smith family, mother and daughter and husband, gave their name E.A.L to son Smith, Edward. And so no wonder that what Edward, as a mechanical engineer, did later in his life was making a model using E.A. and L for the spring and for a mass in which he divided the pile. So the stiffness, of course, is E.A. over L. That's the spring. And the mass is E.A.L divided by C squared. That's the whole thing. That's our wave equation. And now you know why we need those three letters in his name. There was a big discussion in the committee, I understand. Should we really use all three letters? Yes, they are most important. E.A.L here, that's the final model he came up with, where he realized we have to use a bunch more segments, maybe a meter long or so. And they are all, these segments, masses and springs. And that you can even use for the cushions and the hammer and the helmet. And then we need, of course, something about the soil, unfortunately. And there, being a mechanical engineer, he thought, oh, well, we need again a spring, and we need a dashboard, like in a car, a kind of a damper to represent the dynamic effect of the driven pile. Well, then the geotechnical engineers came about and said, sure, that elastoplastic soil resistance is nice, and the viscous dashpot, but we do need it to represent the resistance distribution on all of the segments and at the pile toe. So we got our shaft resistance and our end bearing. And Smith was not only doing a mechanical model of the pile, he was able to give us some values to calculate with. The one value that we needed was the so-called quake. And a quake is related to what the pile driver observes when he's in the field. The quake is practically the rebound of the pile. You push the pile down with a hammer, and then it rebounds a bit, and they call it quake. And indeed, we see that spring contracts and then expands, and elastically with an amount quake, which is Q, and then the capacity cannot exceed the value RU, that we have from geotechnical formulas. So that is how it looks then for both shaft on the left and toe on the right. You have there the elastoplastic increase of the resistance as the displacement of the pile segment goes down. And Smith gave us values of 0.1 inch for the shaft and for the toe. And Smith piles were all relatively small. They were the largest diameters were probably 14 or 16 inches usually, and the 0.1 inch is pretty good for that. Now that we went to larger piles, like a 36-inch concrete driven pile, we have to use the diameter as a criterion for that quake value. And also for the dashpot, he gave us the so-called Smith damping factor, which is 0.05 for the shaft, seconds per foot. And it's a little bit of an awkward model that he uses. One has to multiply the damping factor, which is in seconds per foot, with a resistance to come up with the actual damping factor. So it's not truly linear, but for those Puritans who want it truly linear, we also provide now the model with an RU instead of an RS, and so then it's a truly viscous damping. But no matter what we do, we always go back to Smith's model. It is really the one that works most reliably under all kinds of circumstances. Not very sophisticated, but reliable. And of course, there are possibilities of having some errors still. Anyhow, he wrote about it in a 1954 paper, and then later, or actually earlier, he wrote a paper after a seminar at IBM, and the seminar was in 1950. And in the seminar, they discussed how this wave equation was to be programmed. And I have heard through George Goebel that this was actually the first engineering non-military program that has been written for an electronic computer. So he was way ahead of everybody else there in the civil engineering community. And he later then, of course, published that also in Geotechnical Engineering Journal. And that 1960 paper is the one that's frequently quoted today still. Well, in the earlier times, the the solutions had been done with the superimposition of waves, like Saint-Venant solving here the pile stresses under a rigid mass. And that was then written up in theory of elasticity by Timoshenko, and it was really my Bible when I worked on the interpretation of data. Boussinesq, for example, used it also earlier in 1883 to come up with something that related the mass of RAM to pile weight ratio, and that formula was later still used frequently as a rule of thumb for how big your RAM has to be when you're driving a pile. But that was not considering yet the tension stresses that could develop in concrete pile. Fisher used this upon the recommendations by the UHAD. In 1983, he made a presentation of his graphical solution, quite complicated and quite sophisticated. He did with a graphical solution what the wave equation solves for us with a computer today. But of course, it took a professor. It couldn't be done by many people. And so thing that came out of it, though, that's useful for us is this graph of time and length, which is very instructive on how the waves travel down the pile and return. And we used that then, and I used it in my thesis in 1970 to interpret the data, like on the right-hand side, you see the force and velocity data that we collected, and then out of that came the upward wave and the downward wave. And that leads then to the development of the case method, and then also later for the signal matching with this method of characteristics, as is being called, where instead of E.A.L, you are now using E.A/C, the impedance of the pile. And so you use pieces of E.A/C, and other people, particularly in Europe, are using that solution for their wave equation analysis. But we use it for both the case method and the CAPWAP method now, after initially using also for CAPWAP the Smith solution. And so you see on the right-hand side, in the upper right-hand corner, for example, a matched wave-up curve. Being in Texas, I should mention all of the work that has gotten into the Smith solution at Texas A&M by Sampson, Hirsch, Lowry, and others that did a thorough work on checking the method and the parameters that go into it, and that really helped to get this, get the attention, let's say, of the highway departments, the Texas Transportation Institute, and the Federal Highway Administration on the power of this solution. And they did also plenty of capacity correlations. Coyle and Gibson did some interesting work on trying to get the damping factors by impact loading triaxial models, and then getting the ratio of the dynamic to static resistance versus velocity of loading. And so that then was picked up by quite a few different researchers and thought, now we have a better damping model. But after all the efforts and the years that were into it, we all went back to this old Smith model because it's just so much more practical and easier to use. One thing that Smith had not done and that hadn't been done yet at the Texas A&M program was doing something for the diesel hammer, which is quite a different animal. And so in a dissertation that came out in 1975, Dave Rempe, who worked as a graduate student for Tom Davison at the time, came up with his Diesel 1 program. And so then in 1974, the Federal Highway Administration did kind of a competition and between TTI and GRL, at that time Global Associates still. And they said, well, write us a program now that includes the diesel hammer and also compare it with field measured records. And in that regard, we were kind of ahead. We had a lot of records already taken under impact hammers on pile tops, and they consisted of force and velocity, and were able to machine process them. So both institutions were actually awarded this contract, and both programs were developed. We called ours SWEEP. And so in 1976 already, we were able to present a program along with the necessary documentation, and we gave seminars already. Should mention the help that we got from the FHWA and also the New York DOT. For example, Paul Bailey was a great help in checking the program. So Then in 1988, the FHWA decided, well, the government is not in the business of maintaining programs. All the time something new came out, new hammers came out that had to be put in, new findings were made, the computers changed and had to be, the programs had to be adjusted to that. So at that point, then the FHWA let us continue to develop and maintain the GRLV program. Well, let me give you a few little stories here. First of all, about the capacity assessment. That's, of course, one of the things that wave equation was supposed to do. It's supposed to give us a better formula, and it does. The formula, the dynamic formula or energy formula, as it was called, is very simplified. But if you create with the wave equation analysis a bearing graph which relates the capacity to the blow count, then you can go in with your known blow count from pile driving and read the capacity of the pile. Now you will have to apply a certain factor of safety to it, which has been 2.75. Right now we would use an ASCE to safety resistance factor of 0.5 and then use that capacity with 0.5, and it has to be greater than the factored loads in the new LRFD method of the ASCE specifications. Well, in 1972, we then had this memorable demonstration. The university, the Purdue University, had organized a conference, a specialty conference on foundations, and George Goebel, he suggested that we do at that time in Lafayette, Indiana, a demonstration, and people were invited to a field demonstration of pile driving, an H-pile that had been given by ASCE as a gift. And then there we were, that's Garland Likens on the left and Frank Rausche on the right. We instrumented the pile, and since that time, we have been working together in trust and friendship. George Goebel then organized the rest, and for example, he had sacrificed some Purdue graduate students to do this, what we call load set diagram on the pile while pile driving is going on. So they pass a pencil along a piece of paper while the pile moves. And then we connected our instruments from along the pile. And then came Professor Leonard and said, well, hey, can't you get the residual stresses too? And we thought, oh my God, now residual stresses, this is tough to measure. That is, you need very precise measurements. And well, we hope we can do that. So we worried about that. Anyhow, the demonstration started with all our wires connected and our first pile driving analyzer connected to that thing. And then George Goebel was reading that thing, and of course a downpour started. Reminded me of the Dallas downpour yesterday, where, you know, have everything now set up outside, and we had to push the tape recorder under the car and out of the rain, and had a little bit noise in the lines because there's no water getting in there. And so he came up and he looked at this little output from the pile driving analyzer, which was still called pile capacity computer, and then read a number, once 145, a little bit later 175, and that was in Kips. So, well, the pile driving was done. and the rain was over then, of course, right at that time. And then a static load test was set up for the next day, static load testing. Here I might mention is Hal Hunt, that some of you may still know from one of the organizers of DFI, who had interviewed me at the time. He wrote a newsletter for DFI at the time, was before at Engineering News. All right, so then we did this load test also. Everything has been written up by Goebel, Kovacs, and Rausche. William Kovacs was a graduate student no, he was assistant professor at the time at Purdue. Later, he had quite a few battles with George Goebel when he was at the Bureau of Reclamation about how to properly measure the energy in an SPT rod. So they were working together later for a long time. He was going pretty high up, I believe, in the Bureau of Reclamation later. And, well, so we had gotten, of course, SPT data here. And that is the black line on the left, and then the dashed line is the actual blow count. No, it's just the other way around. The dashed line is the SPT. Black line is the driving log. And then Dave Rempe looked in his chart that he made, his bearing graph with his Diesel 1 program. And for the 40 blows per foot at the end of driving, he came up in his chart at 166 kips. Had he used the old Smith program, it would have been 180 or something, or 175 or so. Anyhow, the load test then, the day later, showed 163 kips, so that was quite successful and amazing. Now, of course, this capacity is the Davison capacity, and we know that capacity is something undefined. There are various definitions for it, so it's also a little bit of lucky, of course. Well, diesel hammers have become more and more important, and those are animals. Those are not just machines. They do what they want. You put some diesel in, and they might jump this high or that high. For the closed-end hammers on the right-hand side, you have to have a so-called bounce chamber pressure gauge on them to know what the jump height is inside of this hidden thing. On the diesel hammer, the open-end one on the left side, you have to kind of see, is the ram coming out? And it's good. If it's not coming out, then you don't have much resistance, probably. Well, you have to study that, of course. You have to do that accurately. And there is Professor Goebel here sitting up there on the 45-degree one-to-one leads. Thanks to McKinnon, he got a little stick mounted to this lead so he could comfortably sit right next to that hammer while it was exploding and see on the jump stick up there how much the stroke was so that he talked into his tape recorder. Well, that crazy engineering feat produced then data that we could use later in the so-called saximeter formula that we now use in that little instrument that times between hammer blows and converts that to stroke for open-end diesel hammers. It also helped us in our check of the wave equation analysis. Well, another gentleman who supported us a lot was Otto Kammerer of Palco, here in Texas again. He did a lot of tests for us on his test grounds, and he didn't very much about the neighbors around him. That the thing was within actually this test area within a area where people tried to live peacefully. And we measured pressure there and on these hammers. Now, we did that also on a few other occasions on other hammers, and that was very helpful, again, in our development of the diesel hammer model, which consists of practically a Smith E.A.L model of RAM and the so-called anvil or impact block inside, plus the driving system underneath. And then this pressure that develops in the hammer is then modeled with 3 different phases of compression, combustion, and expansion. And there we need these measurements, that help us to come up. Well, why doesn't it go backward? Oh, okay. That come up with the pressures that we have computed, and then a potential correlation with actual measurements on the pile top, like you see on top, the forces that we had measured on a diesel hammer. So as you can see for a closed-end hammer here, we also had a pretty good agreement. On the right-hand side now, the plots from our newest GRLV14 program that shows quite nicely the forces as they were on this 1975 job in Cleveland, recorded on the Link Belt 520 hammer. Well, capacity is not everything. One of the important things that E.A.L. Smith had to do for Raymond was determine the stresses in the mandrels, because apparently the mandrels used to break, particularly on points that were pinned together. These things were 8 feet long typically, and were very heavy pipes, and these pipes had to be held together with a pin, and there was some slack. And already at that time, Smith modeled and coined this term slack in the pile. So it's really a pile that allows for some tension between segments. So now I'd like to show you a little timber pile example where we had also some soil boring, some probably SPT, a Vulcan #1 hammer though, and that was in Louisiana. It was pretty recent, actually. I mean, for me, recent. It was like 5 years ago. And there on the construction side, we had a little bit of a stress problem. These piles were 60 feet long and only had a 7-inch diameter tip, and they went into a dense sand. And so the driving criterion was actually you had to get the pile down, but it shouldn't get more than 30 blows per foot. And so I checked it then with a wave equation analysis, and sure enough, on the right-hand side, you can see the black line is the stress versus pile length. And you see, because of that small diameter at the bottom, it increases to very high values, around 2 KSI, where the ASCE would allow us today for southern pine only 1.38 KSI. Well, this was an interesting project, not only because a pile was subjected to high stresses, a non-uniform pile, but also because they put a follower on top later, because it had to wind up about 10 feet or so below ground, and then there was a pump station later built on top of it. And so this is the follower on the right-hand side. It's a steel follower on a concrete pile, so it becomes a pretty involved model that we had to use. And it's always a question, you know, what does the follower do the pile, and will we get energy losses, and what are the stresses in the pile underneath? And we are able to analyze that pretty rationally with a slack again between pile and soil, pile and follower. And of course, then the follower goes also into the soil a piece that we have to consider. And we use then the model of Smith. And I must say that this is something where the Smith E.A.L. model is really superior to the other models of like the characteristic solution, because it allows us to make a really realistic assessment of a somewhat nonlinear event. And so the results here, I don't know if you can see these numbers quite well, but they show you where in that red box the forces and stresses are shown. The stresses on the compression stresses on the second from the right column, how they go from the 15, 16 KSI in the steel to 1.6 KSI in the wood. But on the other hand, the energy decreases gradually. There is not much energy loss in that slack. So you can see there quite a bit. This plot here shows you the stresses in steel on the right top and timber on the left. Well, you know, residual stresses is something that has become more and more important. And as I mentioned, Professor Leonard already pointed that out in 1972, that we should do something about that. For long, slender piles, it's important. By the way, it's not a beautiful picture, nothing to do with my talk, but Mohammed gave it to me, so I thought, and he gives me a lot of good pictures from the construction site. I wanted to share that with you too. Anyhow, there's a train right next to the driven pile, and that's an exciting event. And no vibration problems at all, you might be glad to hear. So, well, Holloway already in 1975 had done a thesis using the Smith TGI program, introducing the residual stress analysis. Residual stresses develop in a pile because when you drive the pile down, you push it down under a hammer blow. It tends to rebound a bit, but the negative resistance forces along the shaft that develop then hold that pile down, keep it in compression, so when the next blow comes, the pile is already compressed and doesn't have to be compressed any further, and then moves relatively easier into the ground. So that makes actually the pile driving a bit easier, makes the pile stresses a little bit higher. So it's an important thing, and E.A.L, a graduate student at Colorado University, where Goebel had moved in the meantime, did a model and put that into the wave equation, in our wave equation program. They called it first CU-WEAP, and then later we put it into our GRL-WEAP. Residual, the name is used now variably for different things. Some people call the residual displacement really the final set after the rebound. Others call residual resistance a part of the friction fatigue analysis, which I will be mentioned soon too. Well, in any event, for the Becker rod, for example, for the Becker penetration test, residual stresses are actually something important. The Becker test is designed for very dense soils where the SPT rod cannot penetrate. And so the Becker test is used primarily to evaluate the soils of dams for liquefaction. It is 6.5 inch diameter, heavy walled pipe, closed-ended, driven with a closed-end diesel hammer, an ICE 180, which drives about 90 blows per minute, and is so a very convenient system to obtain a blow count, which is called N30 then, because it's normalized to 30% of the rated energy of that hammer. Like the N60 for the SPT was normalized to 60% of the SPT hammer. So they drive this thing down, and lately more and more measurements are made. Now, also at the tip. And because it's really important for evaluating the blow count and the liquefaction potential from the blow count, how much force or energy get to the pile toe. And you see here a graph, if we do a bearing graph for the Becker test with RSA, with residual stress analysis, it's the black line on top, and it shows you that it gives you a little bit higher capacity and also a little bit higher stresses. Those are the black lines underneath. So with these measurements now that are being done on top and toe, you have to be sure you interpret them correctly. And here is the resistance distribution from our analysis again, from our wave equation analysis, showing also the end bearing, something more than 40 kips here actually, as evaluated first with a red line by the measurements and with a black line by the RSA analysis. And that's something that, of course, Bengt Felenius had been warning us against, always not to interpret wrong our measured data because of the residual stress effect. So one has to make this correction with residual stresses, and either we can do that with a CAPWAP analysis, or we can do that with a wave equation analysis. If we go back to our Purdue test again, and we didn't do it at that time, but we can take our forces, the right side, measured in the pile, and correct them with the residual stresses that we have measured at that time, and seem to make sense. Now the green line is when we do that with a wave equation with residual stress analysis, and you see then the residual stresses in the pile. CAPWAP shows something similar. One of the differences at the very toe of an H pile, of course, we are not too sure over which distance the plug actually has its effect getting into the steel itself, and we measure force at the steel. So there's always a little bit uncertain how much force we really have at the very toe of that little bitty steel edge. Okay, I have to mention the drivability analysis, and here's Dr. Lee Quinn, who tirelessly is programming our program to expand on the drivability analysis, which means that in addition to the bearing graph and the so-called inspector's chart, we have now a third analysis type in the program, which is the drivability, and it has become very popular. Everybody around the world wants to do a drivability analysis. They're not so much interested in the bearing graph anymore. They want to know how many blows will it take to get the pile in, how long does it take to get the pile into the ground. So what it takes, though, is that we do an accurate static analysis of the soil. And in a way, we're kind of doing the opposite of what has been done at Smith's time, where he said, well, we don't know what the soil does, and static analyses are unreliable. So now we're saying, well, we can use them, those static analyses, to get us a long-term resistance, and from that we estimate a so-called static resistance to driving, the SRD. So we reduce that in general, that long-term resistance from the formula, and then we get a resistance that we can subject our Smith wave equation to and get our blow count. Now the SRD is calculated typically with a setup factor, which pile drivers know. When they do a restrike, they have more resistance than at driving. The ratio is the setup factor in very global terms. So we need something that tells us what the soil is doing. We can use the much maligned SPT test that everybody says, no, it's not very accurate. We can use what everybody praises, the CPT. We can, of course, in Texas, we would use the Texas penetrometer, the heavy one, right? And then we can use grain size analyses, friction angle, and undrained shear strength, and then, of course, the soil weight gamma. And we need the water table also on the soil type to be able to do something. And here comes the SPT, always helps us with the soil type. For the CPT, we have to kind of guesstimate what the soil type is. So we can do that again with our Purdue example. We had an SPT. We can divide the soil into these layers that you see on the right-hand side from the SPT. And then we see that our static analysis, it's our SA analysis, gives us 177 kips. So not bad. We had, 166, 163, 177. That's all pretty close. And that is a long-term capacity. So actually, but in the sand, not very substantial. There is some loss of resistance during driving. We use 83% typically during driving. And so then we can do our calculation of unit shaft resistance, unit end bearing quakes, and damping all versus depth, like in this table, and come up with, on the left-hand side, capacity versus depth and blow count versus depth. And if we look at this together now, blow count and driving log, the driving log is in blue, the blow count from our wave equation in red, you see they agree quite well, so not too bad. And that with a stupid SPT test, But of course, these were relatively simple circumstances. Had we used the full resistance, the long-term resistance, you would get the dotted line, you would get a little bit higher blow counts towards the end. Now, there are plenty of error sources, and I don't want to go into them all. Of course, one is hammer performance, all of these quake and damping factors, and the resistance versus steps in the SRD calculation method. If we look at all those methods that we have now in the program that use SPT or lab constants, and plot the long-term resistance, those are the solid lines on the left-hand side, then you see that they can give us quite different results for capacity versus depth. The black line being what FHWA used in their driven program, and it's really using the Nordland and the Tomlinson method. The lowest value was the SA method that we usually use, our SPT-based SA method. And in between, not too far above that, we have the API methods from the American Petroleum Institute. The newer one, the older one, they're almost the same for non-CRP, why do I say CRP? CPT methods, cone penetration test method, non-CPT. So they are relatively close together with the Bowles method, which is the one where we only give it like medium sand or stiff clay. Another method came up, and it is particularly in Europe now quite fashionable, and it's called the friction fatigue method. Actually, it had been introduced already in 1977 by Herima for offshore work. And it says that you can wear down a soil. You can reduce the soil by fatigue. So those elements that are subjected to a lot of pile driving of the soil, they fatigue more than those down below that just experienced a few hammer blows right now. So between those highly reduced elements and those further down, we have kind of an exponential decay of loss of resistance. And so that's in very short terms what they proposed, and Arm & Hammer in 2001 has put that in a very concise form with all of the necessary equations, and so many people want to use that now. So we had to use it also. And here just a demonstration of this exponential decay of the resistance in a residual, not a residual, in a friction fatigue analysis. So there is a blue line in there, a dotted line, vertical, and that shows us the SRD calculation from our setup factor, which is done really uniformly over a soil layer. In contrast, the friction fatigue method does this exponential decay. And Arm & Hammer gave these equations for that E function, and they also gave then very specific formulas based on the CPT test that are practically a beta method for sands. And there is, of course, our cone resistance QT in that equation. What is interesting is if they use pretty much a very high resistance at the shaft, initial resistance as they call it, based on the cone penetration test, then they use a reduction factor of 5 for the sand. We use only 1.2 for our standard setup method. So they use a very high initial resistance, but then they reduce it very sharply down by a factor of 5, near the grade, some distance above the pile toe. They did a lot of correlations, and they also suspected to use an upper bound to be safe of 25% higher than the normal analysis. Well, if we do that for our Purdue example again, we come up with this black line now, which is a little bit lower towards the end of driving, and that is what friction fatigue is all about. When you drive the pile deeper and deeper and deeper, you may not gain all that plunge flow count anymore. And we have observed that frequently in the Northwest, for example, that you drive a pile and it doesn't change the blow count. It keeps the constant blow count throughout driving. So that might be one way of improving that, that prediction of very long piles into very dense sands, as it seems. Okay, well, let me just quickly show now also, I have shown you the non-CPT methods. I want to show you a few CPT methods. I digitized myself by hand with a red line this electronically recorded QT and FS, cone penetration resistance and friction sleeve resistance. And I wanted to compare what comes up as a result of that. That jumped again, but it doesn't go back. So, yeah. And, well, then we have to assign a soil type. We do that via Robertson. That was that previous slide. It jumps around. According to this chart. And then we get the soil types that way automatically, or you can do it by hand. And so then I did the Schmertmann analysis, and you see that my hand digitizing and the electronic one are pretty much the same. That's Schmertmann CPT method, giving you this resistance during driving. And then if we compare that with all the other methods that we have available now, the red one being the ANH analysis, this is friction fatigue analysis. And then the other methods are primarily the 4 CPT methods that the American Petroleum Institute is recommending, then you see there's quite a bit of difference between these results. And if we calculate then the blow count from these, then you see the blow counts on the right-hand side, they can easily differ by 150%. So it is most important, and when selecting these methods, that you know what's going on locally. And you may come up with your own preferred method that works best for you. Because if you go into a new area, you might stray away from the real result quite a bit with this analysis. Interesting, the resistance distributions based on these soil type presentations from Robertson, and you see on the left and on the right-hand side, you see those that occur during driving from ANH, from the friction fatigue people. All right, so we have our Smith E.A.L analysis, and then we put in a diesel hammer, and then we put in an inspector's chart, and then we put in a two-pile analysis and a two-toe analysis, and then we put in a residual stress analysis, and then we put in a drivability analysis, and then we added on some variable cushion analysis, some variable stroke and energies, some variable efficiencies during driving, add-on considerations, variable pile length, along with the possibility of setup during driving in a kind of an interruption of driving. And then we need the static analysis in our program. This is our SPT analysis. This is the soil type analysis. This is the CPT by Schmerdman. This is the API, the old one. Oh, in the meantime, let's do a vibratory analysis too. Forgot about that. And then comes the FHWA with the inseparable Tomlinson and Nordland methods of calculating resistance. And then comes API 2 with those four fearless one fellows there, Imperial College, Fugro, and University of Western Australia and the Norwegian Geotechnical Institute. Well, you can get a few different things. Right now, we of course had to add also the friction fatigue analyses to that because it is all needed. And then we needed to count the number of stress cycles for fatigue analysis of the pile material. And we needed different hammers driving the pile. So you can start with a little hammer and then come in with a big hammer on top of it. And then we have bottom drive even to do. What's next? So it keeps on going. There's more and more to be put on. And if you see that picture here, of course, things are developing. Nothing is stopping. Imagine this 7-foot diameter hammer there driving this 25-foot diameter pipe down there. What kind of a helmet plate that is? Is that really just a little rigid mass anymore? I don't think so. Well, I think we have helped with the wave equation analysis, and Smith did so. With quite a few of the developments that have been going on in helping to check out what equipment would work in a certain area and what not. And then reversely, of course, the industry has driven us too. With these developments in the driving system area, as well as the developments of the computers, of course. And today's programming, what could be done in one night with a Fortran program in the old times when I did that, takes probably several weeks now from a highly specialized person, because it has become quite complex. One important thing, and there comes, of course, then the thanks to PDCA, and here, like on the PDCA professor's course, education is most important. and educational events are most important. And we have all worked together. DFI has done a lot, and PDCA is doing a lot. And you know, ASCE too. But here it's another DFI event, and when we thought we don't do any more demonstrations because something will always go wrong if it can go wrong, that was one too here. It was actually a little pile that was driven in front of the audience, except it didn't go in the ground. It just stayed there. 150 blows per foot for the first foot or two. So everybody left then after the initial event, and George Goebel was sitting there and counting blows very diligently. Thank you, IFCEE. Thank you for arranging this tremendous conference. Thank you, the 4 different organizations that have been doing that. And of course, thank you for the award. Thank you, PDCA. Highly appreciated. And also for honoring E.A.L. Smith. I think he has not gotten in as much honors and respect as he should. Working for a contractor, he is one of the few who really did outstanding work, and that's why we also 2 years ago, or no, several years ago, decided that he should be honored. And then, of course, thank you also to my colleagues at GRL and PDI. For many years, they have been doing hard work, also in the organizations, the various, you all know various of our people that have been doing committee work and that have been working hard at the same time in the field and in the office. I thank also friends in the organizations here and my family for letting me go, not only to this event, but to many other events and to many construction sites early in the morning on July 4th, over Christmas, and what have you. So thank you all, and let the energy be with you, okay?